So, in the last lecture we introduced the concept of point groups. Which number 32 in 3 dimensions. So, we started in this lecture, we will enumerate these point groups in a rather systematic fashion. We saw that the first groups are the cyclic groups, cyclic point groups given by the general symbol Cn, where n is 1, 2, 3, 4 and 6. So, we have C1, C2, C3, C4 and C6. So, these are the cyclic point groups which are abelian. These are the simplest. In addition, we have the M, the mirror, which is also given by the notation Cs, and I or 1 bar, which is Ci, the inversion. So, I use the Schoenflies or the international symbols interchangeably. So, we have, for example, if you take C2, the point group C2, the elements are the identity element and then the C2. These are the elements, whereas for C4 the elements are C4, C4 square, which is really C2, and C4 cube, which is C4 in the clockwise direction, and so on. Similarly, for a mirror, this is, and for an inversion, the elements are we then went on to add these mirrors to the various axes to get new point groups, and so we got the point groups 2 by m. This is also shown as 2, this is shown as 3, this is shown as 4, shown as 6. These are alternative notations. So, we get the point group 2 by m, which is a direct product of C2 and m, and then we have similarly 4 by m and 6 by m. We can also get, just like we have 1 bar, we can get other point groups like 3 bar, 6 bar and 4 bar. We can also add mirrors parallel to the rotation axis, and that would lead to point groups which are new, such as six mm, 3 m and so on. So, we get various point groups by the addition of mirrors either perpendicular to the rotation axis or parallel to the rotation axis. So, these are known as the CNH for a horizontal mirror plane and CNV for vertical mirror planes. Then we said that we have the so called dihedral Dn, the dihedral point groups, which are got by combining rotation axis. This is also known as D2, and you get 3 2, this is D3, and 4 2 2, 6 2 2, this is D4, this is D6. So, we can go on like this to get additional point groups. Now, we can add mirrors to these to get things like 2 by m, 2 by m, 2 by m, 3 bar 2 by m, 4 by m, 2 by m, 2 by m, and 6 by m, 2 by m, 2 by m. So, these are known as the DNH, where you add a horizontal mirror to the dihedral point groups. Similarly, you get also additional point groups by having DNV. We can also have diagonal mirror planes giving rise to DND. All these are axial, they have a rotation axis, whereas we also have, in addition to all this, the cubic point groups, and a cube is an object of very high symmetry, which includes the symmetry of a tetrahedron and an octahedron. So, you have T and O, which are also known as 2 3 and 4 3 2. Let us draw a cube and it can be readily seen that by joining these and the vertex opposite to this triangular plane, you get a tetrahedron. So, that is the one which has obviously a threefold axis and twofold axis of symmetry, whereas the same cube is also consistent with octahedral symmetry, as can be seen by taking the midpoints of these sides So, one can see how a cube is has implicit the octahedral symmetry, and the octahedral symmetry is consistent with a fourfold axis and a threefold axis and twofold axis. So, it is to show that it is also known as 4-3-2, and then one can also have additional mirrors in a cube. For example, it is clear that there are mirrors present everywhere. So, addition of mirror symmetry gives rise to additional point groups like 2 by m 3 bar and then 4 by m 3 bar 2 by m and then 4 bar 3 m. So, this is the point group of highest symmetry among the 32. It is known as OH, the octahedron with horizontal mirror planes. So, that would complete the enumeration of the 32 point groups. Now, these symmetry elements are all shown in the figure via the technique of stereographic projection. In this figure, you also see a distribution of these various point groups among the so called crystal classes. What are these crystal classes? These crystal classes are numbering 7. They are best understood by simply enumerating them in order of ascending symmetry: triclinic, monoclinic, tetragonal, well, trigonal, and then you have hexagonal, orthorhombic, and cubic. So, these are the crystal classes, and you can see that the triclinic does not have any degree of symmetry, and the point groups 1 and 1 bar fall in this. Monoclinic is 2 m and 2 by m. All these have a principal two-fold axis, and then you have trigonal. Similarly, you can see the various these various symmetry elements associated with these are also shown by what I explained as stereographic projection last time. So, the distribution of the 32 point groups among the different crystal classes is shown in the next figure. Now, the crystal classes have the different characteristics with respect to the shape or the description of the unit cell of the crystal, and as you can see, triclinic does not have any degree of symmetry in that, in the sense that the 3 lattice periodicities in the 3 directions, crystallographic directions, need not necessarily be equal, and this is also true for the interaxial angles alpha, beta and gamma. Whereas, in the case of monoclinic, you have A not equal to B again. So, this is triclinic and so on. So, A not equal to B not equal to C, alpha equal to beta, it is not very clear, gamma equal to 90 degrees. Then tetragonal has A equal to B not equal to C. A tetragonal lattice is something like this. So, it is a square base and a long parallel, like a rectangular parallelepiped. So, A equal to B not equal to C, but the interaxial angles are all 90 degrees. Then you have cubic, which is the high symmetry, and here all the 3 parameters, lattice parameters, are equal. So, also the angles are also 90 degrees, so that the axes are orthogonal to each other. Then you have the hexagonal, which has a hexagonal symmetry, and also the orthorhombic, which I have already shown, and then the trigonal or rhombohedral. So, these are the various classes, and the distribution of the various point groups is also shown. Now, we have discussed point group symmetries and the classification of the different crystals of different classes and the distribution of the various point groups into these crystal classes. Next, we have to consider the other symmetry which we already mentioned, namely that of translational symmetry. So, we have to see what happens when we add translations to the symmetry elements of the point groups of a crystal. Then we arrive at all the spatial arrangements that are consistent with the symmetry of the crystal. These are known as space groups. So, the space groups are derived from the point groups by adding translational symmetry elements in 3 dimensions. In order to discuss space groups, which are 230 in 3-dimensional space. There are 230 space groups in 3 dimensions. In order to discuss this, it is necessary to know the different types of lattices which are possible with a given unit cell belonging to a crystal class. So, let us look at this first. These lattice types are known as Breve lattices. They are 14 in number. For example, in a cubic crystal, you have the simple cube like what I showed here. A simple cube is just one in which there are atoms or molecules only at the vertices of a cube. So, it is a simple cubic lattice. Among the elements, polonium is the only element which is known to crystallize with a simple cubic arrangement. This is because the simple cubic structure is very open and the atoms tend to get into more tightly packed structures. So, these tightly packed structures are got, for example, by adding an atom or molecule at the body center of the cube, then the simple cube becomes a body centered lattice, body centered cubic lattice, BCC. Or we can also add atoms at the face centers. So, if you have atoms like this, then this is a face centered cubic lattice, FCC. So, these are much more tightly packed than a simple cubic space lattice. Many metals form body centered cubic lattice, others have the face centered cubic lattice or sometimes the end face centered. Only one pair of end faces get centered. So, these are the different Breve lattices, and figure shows the various space lattices belonging to the different crystal classes. For example, here we have the Triclinic primitive lattice. A primitive lattice is one in which there are atoms only at the corners. Then you have a monoclinic primitive and a monoclinic body centered. Then the orthorhombic has all possibilities: orthorhombic primitive, orthorhombic body centered, orthorhombic face centered, and orthorhombic end face centered. Then you have a hexagonal and a rhombohedral lattice. We then come to tetragonal primitive and tetragonal body centered, as well as I already said, cubic primitive, cubic body centered, and cubic face centered. So, these are the 14 lattice types. Now, when we combine translation symmetry with symmetry elements as the 32 point groups, we arrive at the 230 space groups, which describe the complete symmetry of the atomic arrangement in crystals. When a translation is combined with a rotation, so you have a rotation axis and then you perform the rotation, bring it say here, and then take this atom from here to a position by combining a translation. The rotation is followed by a translation. This is amounts to what is known as a screw axis. When a translation is combined with a mirror symmetry, then we get what is known as a glide plane. A mirror plane combined with translation is a glide plane. So, translation, screw axis and glide planes form the elements of space groups. So, for example, for a two-fold axis, we can have a translation by half the repeat distance along the rotation axis, as shown in the next figure. So, you have an atom which is brought into rotation and then translated along the rotation axis. So, that is a screw axis. Similarly, shows a glide plane where there is a mirror symmetry and then a translation. The translation in this case can be either in one of the sides of the mirror plane or the other side of the mirror plane, or sometimes along the diagonal of the mirror plane. So, you have different types of glides and screws. So, in the case of a two-fold axis, we can have a 2-1 screw or a pure rotation axis, two-fold axis. Whereas, in the case of a three-fold axis, you can have 3-1 or 3-2 or 3. 3-1 means a three-fold axis of rotation followed by a translation parallel to the three-fold axis by 1/3 the lattice periodicity, whereas this one gives you a translation parallel to the axis by 2/3 of the periodicity. This is a pure rotation axis, and so on. So, you can have different screw axes like this, and as I already said, in the case of the glide planes, you can have glide planes either along, for example, if AB plane is the mirror, then it can be an A glide with a translation component along the A axis, or a B glide. This is an N glide, a diagonal glide with a translation component of A plus B by 2, whereas this is A by 2, this is B by 2, the translation component. A D is a what is known as a diamond glide, which can have a translation component of A plus B by 4. So, these are the various possibilities of screw axis and diamond glide planes. So, now we can talk about space groups and their nomenclature. Nomenclature. The symbol for a given space group, the first letter stands for the type of lattice. For example, whether it is a primitive lattice or a body centered lattice, face centered lattice, or n face centered lattice, for example, A face centered, and so on. So, you can have A or B or C face centered lattices, and then you can also have rhombohedral lattice in the case of a trigonal symmetry. So, the first letter in the space group symbol stands for the type of lattice. Then it is followed by the point group modified according to the translation element. For example, whether it is a screw or a glide. For example, let us take an example and illustrate this. P21 by C. This is the symbol for a given monoclinic space group. This means because the corresponding point group symmetry is just 2 by m. So, that is a monoclinic point group. So, this is a monoclinic primitive lattice in which the two-fold axis is replaced by a 2-1 screw. A two-fold axis followed by a translation component of b by 2 along the unique axis, two-fold axis. And then you have a glide plane perpendicular to the b axis, the unique axis, two-fold axis, and this has a translation component of c by 2 along the c axis. So, it is a c glide. So, these are the elements which go to make up the. So, it is a primitive monoclinic space group. So, this is how you understand the space group symbol for any given space group. Next, we come to the another important characteristic of crystalline solid, which is an isotropy. So, we talk about solids are in general anisotropic. Isotropic means it is the same behavior in all directions. Anisotropy means that the properties of the crystalline solid can be different along different directions. So, the physical properties depend on direction. So, it is very important to have a mechanism, standard way of representing different directions in a crystalline solid. For example, we know double refraction, which means that the refractive index has two different values, one along one direction and another along a plane in a plane perpendicular to that direction. So, you have n1 and n2, two refractive indices. This is a standard example of anisotropy. So, it is very important to specify the direction. How do we do it? A given direction is always associated in three-dimensional space with u, v and w, which are the direction cosines of this direction with respect to the crystallographic axis. So, the set u, v, w, which are the direction cosines, are used to denote the given direction. For example, in the figure, the different crystallographic directions 1 0 0, 1 1 0, 1 1 1 and 1 1 2 are shown. We also need to describe in a some standard way the different crystallographic planes. How do we do that? For example, cleavage planes, if you take a solid and try to cut it, it gets broken more readily along certain specific directions. So, these are along the cleavage planes, because these planes are more densely packed with atoms. So, how do we talk about the different crystallographic planes? We talk in terms of the intercepts that these crystallographic planes make with the crystallographic axis. So, we measure them in units of the lattice parameters. So, suppose we say let us take u dash A, v dash B and w dash C are the intercepts. Then we take these. So, these are intercepts measured in units of A, B and C, the principal lattice parameters. Then we take the reciprocals 1 by u prime, 1 by v prime, 1 by w prime, and these are reduced to a simple set of integers. So, the reciprocals of the intercepts measured in units of the lattice parameters and reduced to simple integers. That gives the set of numbers which are put together to refer to a given crystallographic plane, and these integers are usually written as h, k and l, and these are known as the Miller indices. So, usual standard symbol for Miller indices is HKL, and the figure shows different crystal planes with different Miller indices such as 111, 110, 021 and 102. It is one useful property for a cubic crystal is that the interplanar spacing is the lattice parameter divided by h square plus k square plus l square. So, this is a very useful for a cubic solid. This is a useful relation to keep in mind. So, we will see in the next class how do we determine crystal structure experimentally using so called diffraction methods, principally by X-rays.